Well, thank you very much, Andrea, for a very extensive and detailed introduction. We met really many years ago, but it's always a pleasure to see you again. So it's really a pleasure to be here with all of you today and to have an opportunity to tell you about very recent experiments that we have been doing in my group at ICFO in Barcelona. And these are experiments that are all unpublished, so there are things that are still ongoing. We are still analyzing data and so on and so forth. So as Andrea said, I work at ICFO. ICFO is in Castelldefels. This is in the outskirts of Barcelona. If you have been in Barcelona, probably you flew to the airport, which is, if I make the pointer work, here. Yeah. Then you have been in the center of Barcelona, in the Sagrada Familia and the nice Gaudí buildings. So ICFO is 20 minutes drive from the city center, and it's just a few blocks away from the Mediterranean Sea. So in my group, we do experimental quantum gases, and we have 3 labs. So the Potassium lab is a lab where we study mixtures of potassium Bose-Einstein condensates with tunable interactions, and we have been doing a broad range of continuum physics, from engineering ultra-dilute quantum liquids that form droplets like the water drop that you see here, to engineering gauge theories, like effective gauge theories for 1D anions in these systems, and more recently supersolidity, which is what I would be talking about. Then we have a second lab, that's a lattice lab, the Strontium lab, where we have very recently demonstrated a quantum gas microscope for superfluid strontium. And then we are starting to set up a third lab, a Rydberg lab, where we want to investigate lattice gauge theories with strontium Rydberg atom arrays. But today I will be talking about mostly what happens in the Potassium lab, and the question that we have been addressing over the last year or so, it's the question of supersolidity. And supersolidity is a very interesting phase of matter. So it gathers the properties of a superfluid, so a system that can flow without any friction and which has one spontaneously broken symmetry, which is gauge symmetry. So it has U1 symmetry breaking. And at the same time, this system spontaneously crystallizes, so it has also the properties of a solid which breaks translational symmetry. So this supersolid is really like a super phase, because these phases are pretty contradictory. I mean, this frictionless flow and the crystalline structure, they seem to be like not playing well together, but you can have a system in principle that can have both. And this is a very cool idea that was proposed at the end of the 60s, beginning of the 70s by Andreev Lifshitz, Chester, and Leggett, and discussed extensively in literature. What all these people had in mind at the time was to take a solid, so the most quantum of all solids, that's solid helium, and have it become superfluid. Yeah? And this is something that sparked a lot of interest. And from those early days on, there were a lot of efforts to see this supersolidity in solid helium. But the evidence for supersolidity in that system has really remained elusive. There have been many claims of seeing supersolidity, for example, back in 2004, just when I was starting my PhD. So that was a topic that I thought about going into. There were the experiments of Kim and Chan, which made claims of supersolid helium, but it turned out that these were actually the other effects going on there. So really, if you check what's going on, the nice reviews, supersolidity is really often considered an enigma. Yeah? That phase that in solid helium is not yet there. But then, because of the interest on combining these two properties together, there was also the idea, if you cannot easily make a solid become superfluid, that one could also take a superfluid and make it gain solid properties. And these ideas were also proposed a bit later, in the 80s, 90s, and were building on the use of liquid helium. And why that? Because if you look at the excitation spectrum of liquid helium, you see that it has this funny structure. So it has a linear part here, a phonon part, but it also has this hump here, which for historical reasons is called a roton. And then this system, this happens at a given momentum scale. That means that if this roton has an energy that actually goes down to 0, it's going to make a characteristic length scale appear in this system. So it's actually going to, if this roton reaches 0 energy, make the crystal spontaneously crystallize at this scale. Yeah. So the question was, can you turn liquid helium also into a solid? But it turns out that there are also technical things, so this could not be done. But it's then stimulated even later the idea of doing that with quantum gases, because at the end, quantum gases are superfluids also. So if you can engineer systems with such Roton maximum excitation spectrum, maybe you can get this Roton go soft, touch zero energy, and then have the spontaneous crystallization and have that without losing the superfluidity. And indeed, if you take Bose-Einstein condensates, there are really a number of systems where you have this type of Roton spectra, and these systems range from spin orbit coupled BECs or shaken optical lattices. These shaken optical lattices were realized in the group of Chengqing, for example, in Chicago, or systems with dipolar interactions where you have magnetic atoms, magnetic dipoles in a Bose-Einstein condensate. This is, for example, a measurement here of the Roton excitation spectrum in the group of Francesca Ferlaino in Innsbruck, or also long-range interactions can be made really extremely long-range, infinite range, if you put the atoms in a high-finesse optical cavity, and you also have such a Roton minimum as measured already many years ago in the group of Tillman-Esslinger. So the question is, can in those systems, in some of them, have this minimum like reaching zero energy and have supersolidity appear? And actually the answer is yes. In 3 of these 4 platforms, this has been observed. And we have then supersolid phases that have emerged in this Bose-Einstein condensate, both in BECs, in crossed optical cavities in Zurich. These are cavity supersolids, in magnetic atoms in Pisa, in Innsbruck, and in Stuttgart. These are the dipolar supersolids, and in spin orbit coupled Bose-Einstein condensates, both at MIT and at JQI. So now you have really this playground of many platforms where you can have supersolidity in BECs. And in 2 of the cases, the case of this long-range interacting supersolids, so the cavity supersolids and the dipolar supersolids, actually these supersolid crystals have been studied in detail because they could make supersolids that were easily accessible. And what they have seen is that, yes, there are common properties. These systems are superfluid and they spontaneously break a continuous translational symmetry. But in the cavity supersolids case, these crystals are very rigid. So they have a period that is induced by the light wavelength, but the mode of the optical cavity. So this can slide spontaneously, but there are some excitations that are not there because of this rigidity of the cavities, while dipolar supersolids have been made in very small systems, but they have some very flexible crystals that have a lot of excitation modes, and they have beautiful experiments where you can really see how these crystals are excited and so on. And the question that I want to address today is what happens with spin orbit coupled Bose-Einstein condensates. So this is one of the really first platforms at the same time as the cavities where supersolidity was seen in BECs, but we know much less about them. And in particular, we don't know about how these crystal excitations are. And actually, there are contradictory claims in literature how they should be. So we thought, okay, well, it would be nice that we do experiments and we try to really understand that from the experimental point of view. So before going on, maybe let me tell you how spin orbit coupled Bose-Einstein condensates work and how supersolidity comes about in these systems. So basically, it's a very simple system. You have a BEC with 2 components. So it will be blue atoms and green atoms in my talk, or spin up and spin down. And you just join these 2 states with a 2-photon Raman transition. And this is really a scheme that was pioneered by the group of Ian Spillman at JQI many years ago. And if you look at the dispersion relation of such a system, what you have, if you go to the proper rotating frame in momentum space here, you have the dispersion relation of the blue atoms and of the green atoms that are spaced by the momentum that it takes to absorb a photon from one beam and re-emit in the other beam. Because when you do this process, you flip from one spin to the other one, then you get twice a momentum kick. So that's why here you have this 2kr that separates them. So this is the situation that you get in the absence of coupling, and this kr is the characteristic momentum scale of the problem, and er is the recoil energy associated to this momentum kick. And if you put now coupling, so you put a Rabi frequency which is not 0, then you will get an avoided crossing occurring here at the intersection. So you will get now atom-photon dress states that I have depicted here that just keep the memory from the original states that you started with, and then you have a lower dress state minus and an upper dress state plus. Yeah? Now, this is what happens if you put very little strength of coupling. Now, if you increase the strength of the coupling, at some point the dispersion relation will look just parabolic, like here. And you can then, if you have a gap that is big enough to the higher dress state, restrict yourself to the lowest one. This is what we will do in the rest of the talk. And you see also in this type of sketches that I do, I have this color scale for the energy here, the dispersion relation of these dressed atoms. This is because you see that the polarization, that is the spin composition of this dress state, is momentum dependent because it keeps memory of the states from which the dress state was made of. And that's why this scheme is called spin orbit coupling, because you're really coupling the momentum and the spin of the atoms. And we did previous experiments, these experiments on gauge theories for 1D anions in this regime of very large Raman coupling, where this dispersion relation is parabolic. But today I will be focusing instead on the regime where the dispersion relation keeps really this double minimum structure. So how is supersolidity coming here? Actually, the point is, if you now put atoms in the two minima of the dispersion, then you see that these dress states, I mean, these two minima, they are not orthogonal to each other, because the dress state in this minimum, it's mostly made of blue atoms, but it also has a small admixture of green atoms, yeah, because it's in a coherent superposition of the two. And in the right minima, it's the other way around. It's mostly green atoms, but with a small admixture of the blue. So these two dress states, actually here in momentum space, they look separated, but in real space, they are all overlapping. So you will have interference of this big blue component with a small blue one here, and the other way around for the green. And that's going to give matter wave interference, and it's going to give some modulated density profile. So this is in principle what you expect for a supersolid. So you have this breaking on translational symmetry. You have this density profile that looks like a crystal, yeah. But at the same time, this system is built from two superfluids. So if it retains superfluidity, it should be a supersolid. And this is something that was put forward very quickly after the first experiments with the spin orbit coupled BECs by Jason Ho. Okay, so now this is in principle all you need to do, make this double well dispersion relation and have the atoms condense in the two minima. But the question, of course, that you have to ask yourself is whether things are so simple. So if you just put atoms in this double well dispersion, where are the atoms condensing? Are they really condensing on the two, or are they condensing in one or the other? And this actually is a game of interparticle interactions. It depends on the interparticle interactions, because you see that what is going to matter is basically what are the interactions of the atoms in the left well, in the right well, and you can have interactions between the two wells. If you have the interactions in between the wells that are weaker than the interactions in each well, it will be energetically favorable to occupy the two. Yeah? And then your system is going to be miscible, and it's going to go into this supersolid phase that is often called the stripe phase, because this density modulation is only in one direction. So the profile looks like stripes. Yeah. But if the interaction between the two minima is large enough, is repulsive more than the interaction in each well, then it would be much more favorable, of course, energetically, to put all the atoms either in one well or in the other one. So you will have what is called a plane wave phase, and this is like nothing else than saying that these two minima, they are immiscible. And then you will have no supersolid. And the question is, what happens in experiments? So the first experiments of Jens Spillmann on spin orbit coupled Bose-Einstein condensates, what they saw using rubidium atoms is that they start with a mixed system. Yeah? So the two spins are getting together. But then as soon as you start increasing the Raman coupling strength, then you see that they start separating, and then you see phase separation. So you're really very quickly at very small Raman coupling, transitioning from the supersolid regime to the plane wave regime. And what you see here is that it seems really that this miscibility is controlled by the Raman coupling. And this is something that we can understand very well in this idea that you have this mixture, let's say, of the two minima, because the interactions of the original states have the values that they have. The system can be miscible, but as soon as you increase the Raman coupling, you're changing the effective interactions of your system to some new values, left, right, and left, right. which can actually lead to immiscibility. And this is just dictated by the spin composition, basically, of these stress states at the location of the minimum. And we can really build some nice analytical model that takes that into account, that can reproduce these things. And what happens is that with the atom that they use in these experiments, just rubidium, you have this phase diagram for your system. So if you just for the moment focus on the central line, so you start with a mixed system, and as you increase the Rabi frequency, it demixes, so it goes out of this supersolid stripe phase. And there is also a second axis, which is this vertical axis, which is the detuning of this Raman process, the two-photon detuning, because you have these two minima. And now, if there is a detuning, one will be a bit lower than the other, and then it will be favorable to just condensing the one that has the lowest energy. And that's actually super sensitive in detuning. You see this 10⁻³ recoil axis. So that actually means that any magnetic field fluctuation, because this detuning is magnetic field sensitive, is going to tend to kick you out also of this phase. So this is going to be very hard to see this phase in rubidium. This phase diagram is telling that the supersolid stripe phase is extremely fragile in rubidium atoms. And also, not only that, also if you check on the horizontal axis, this Rabi frequency axis, then at very small Rabi frequencies also, we are going out of the stripe phase. This is telling you that actually you will have very small Raman coupling, so very small admixture of the other state here. Yeah? And that means that the interference contrast that really comes from the population, like by comparing the populations of the two, we have a really tiny contrast. So for the case of rubidium, the maximum stripe contrast is only 4.5%. So that's also going to be very challenging to see experimentally. So you will have a superfluid with a tiny modulation. So if you see this phase diagram before, maybe you are a bit disappointed and say, well, maybe you should try to do something else. But people are really persistent and wanted to see this phase. So then there were tricks developed to try to make this stripe phase more stable. And there was Wolfgang Ketterle's group had a very nice idea, which was to replace the atomic spins by pseudo-spins. So instead of taking internal spin of an atom, they really took orbitals of a double well lattice, and they made this play the role of a spin, and then you can adjust interactions much more. They did this with sodium, and you get a much enlarged phase diagram. So in principle, you can really see this stripe phase. So here is their new phase diagram, and now the numbers are much more reasonable. There are large numbers here. But it turned out that if you do that with pseudo-spins, with these bands of an optical lattice, you have a very small energy gap between the two. So it turns out that this is a Floquet-driven system with a lot of heating processes associated. So at the end, the experiments technically were limited still to very small values of omega. So our strategy was then to revisit this old problem, keeping atomic spins, but choosing a new atomic species. So first experiments were done first with rubidium, then with sodium, and then we moved to the atom that we use in my group, which is potassium in this experiment. And what you see here is a picture, early picture of our potassium spin mixtures experiment, where we can actually prepare mixtures of Bose-Einstein condensate. Our experiment is a potassium machine, so you can prepare any mixture of the different potassium isotopes. And for the last years, we have been doing mixtures of potassium-41 or potassium-39. For most experiments, the droplets, the gauge theories, we're always using potassium-39, but this time we moved to potassium-41. And why we did that is because we know from some old Feshbach spectroscopy experiments that we had done quite some years ago that at around 50 Gauss, there is a very nice window of scattering lengths, where if you take these two states that I've indicated here, you can have, here in this vertical dashed line, you can have the two scattering lengths of the two states, A up, A down, that are positive, so repulsive and not too different. And then you have very small interactions between up and down. So this is going to enhance the miscibility by a lot. So that's what we do. And then we compute the phase diagram, the same as I showed you before for the other platforms. And this is what you get. And you see that actually this is much more favorable because we won on the detuning axis 3 orders of magnitude in the energy. So that's already very good. But even more important, because this is something that you could still handle with good magnetic field stabilization or things like that, it's the horizontal axis. We won an order of magnitude also. So what this is telling you is that these stress states, they will admix a lot of the other spin components. So you really expect to have very large crystal contrast. And this is indeed what the calculation says. So this is the contrast of this modulated pattern. And you see that it can go almost to 50%. So this, of course, makes it much more realistic to see it in the experiment. So then we move to the lab to try to measure that. Let me just maybe give you some numbers of the experiment here. So first of all, what we do is that we do this Raman coupling at a wavelength that does not create any scalar potential on the atoms, because of course we want to make sure that it's not that there is a lattice due to these Raman beams. Well, they have orthogonal polarization, so we should not, but also let's put ourselves at a wavelength where there is really no potential. And we choose an angle between them of 90 degrees. This is to have the characteristic spacing that we expect for the supersolid, which is given by the momentum that we transfer from this laser. So that gives the distance of the two minima. That is of about 500 nanometers. That's a good compromise experimentally, and that gives us energy scale of 4 kilohertz, which is also a good number. So then we try to measure, but then, I mean, you see this 500 nanometers is still a small spacing, and you have to think that you could have a very nice microscope, but still in each of these stripes, you will have hundreds or thousands of atoms. So this is an optically dense system with small spacing, so it's also not so easy to image. And this is a problem that was already identified in the first experiments, because you need to detect these stripes that are going to be below the imaging resolution. And in the previous experiments, what they did was an indirect measurement. They did Bragg scattering of light. This was the MIT trick that then was also taken over in JQI. So you really take your system where you want to see a supersolid, and you sense a beam. And then if there is no density modulation, then you will only see Rayleigh scattering. So you will see some diffuse light here on a CCD camera. But if there is the density modulation, then you will have Bragg diffraction on this density modulation. And then you will see this coherent spot, this Bragg spot here in the center. Okay? So this is really like in the previous experiments, supersolidity was really inferred from this spot. Yeah? But I mean, we are many years after these experiments, and there were all these dipolar experiments, cavity experiments that had much more direct proof of the crystal. So we wanted to have something better. We thought, I mean, the dipolar supersolids, they can see in situ this crystal. So let's try to do something like that. And then our trick was to use matter wavelengthing to magnify the spatial distribution, really following very nice ideas demonstrated recently in the team of Christoph Weidenberg in Hamburg, that built, of course, on previous experiments from the Joachim group in Heidelberg, and also from the group of Jörg Wallhaven. This was even before I started my PhD thesis. So we adapt this scheme to our Raman couple case. So we start with our system, which has in real space this density modulation. In momentum space, it has these two momentum peaks. And then at t equals 0, we just switch off the Raman lasers to project into the burst states. And at the same time, we increase the trapping frequency of the atoms along the direction of the Raman coupling. And then we let the atoms evolve there for a quarter period until they really come addressed in this trap. And by doing that, we can map the momentum distribution into the density profile of the cloud. And then everything is done there, because then you just need to let things expand, yeah, to magnify this thing and reconvert momentum back into position. And what we do typically is a magnification factor of about a factor of 6, because this is a good compromise between magnifying enough to be able to see nicely this pattern, and on the other hand, having a good enough signal-to-noise ratio, not being too tight. And actually, we do this sequence only along the direction of the Raman beams, at which we know that the pattern is going to emerge, and we keep the atoms confined in the other direction, because that, again, increases our signal-to-noise ratio. So we tested this sequence with standard BECs. We saw the magnification factors that we were expecting, and so on. So we were very happy and also very excited the first day that we tried it with the conditions where we thought that we should have this supersolid stripe phase. And actually, this is what we saw. So you really clearly see that you start with a system which does not break translational invariance. There is no lattice on the atoms or whatsoever. But if you check, you put interactions right, the conditions right, then the system becomes really density modulated. And actually, this is a bit of a misleading image in some sense, because I told you we magnify in this direction, we are not magnifying in the transverse direction, so you don't have to think that we have like an almost 1D system. Actually, our system, if we now stretch the other direction artificially to give you an idea of how it looks in the trap, it really would look like this. So it's kind of a pancake system, which is modulated in one direction and not in the other. And now you can also understand why this pattern is called a stripe pattern, because it really looks like stripes. Okay, so we get these images. We are very happy about them. We tweak everything to have them nicer and nicer. We contemplate them, and of course, immediately you get greedy because you want to do more. Say, well, now I have this density pattern. I can say many things about it. So the first thing is like you integrate along an interesting direction, and you really very clearly see this density modulation, and you see the spacing period of this crystal. And then you may wonder, well, is this like in the cavity supersolids where it's fixed by the laser wavelength? In their case, really fixed by the laser wavelength because it's fixed by the cavity mode. Well, it's like this in single mode cavities. Have multi-mode cavities. Things are more complicated. Then, well, we just measure, and we measure that as a function of the Raman coupling strength. And this is what we find. So we find that really the spacing of these stripes changes with the Raman coupling strength by a lot. Yeah. So we can really say that this crystal period is tunable. And why is that? Actually, this is because if you think in momentum space, the spacing is fixed by the distance in momentum of the two minima. And now in these stress states, if I put more and more Raman coupling, then my avoided crossing is becoming more and more avoided, and the two minima are going to get closer and closer. At some point, it will be a single minimum, as I told you. So then they are getting closer in momentum, so they are getting more spaced in real space. So we can conclude from that this is not like the cavity supersolid, so the crystal period is really not fixed by the Raman laser. But there are way more things that we can say from this type of pictures, and this is actually a single shot picture. So we take an image, and there is this density modulation that appears there, but we can repeat the experiment many times, and we can also extract the phase, so at which position is this density modulation. And if we do that, we see that we really have, repeating the experiment many times, completely random phase of this stripe pattern. And this is what you expect in a supersolid, because it will be symmetry breaking, but you expect the symmetry breaking to be spontaneous. Each time it can appear in any location. Of course, it's very hard to say from this that you have spontaneous symmetry breaking, because there could be technical things. We don't want to make this claim. Yeah, this is a tricky point, but for sure we can say this crystal appears each time in a different location. So what this implies, if you have spontaneous symmetry breaking, you need to have a Goldstone mode associated to that. That means you have this crystal that appears and should cost not energy to it to just slide, move around. And what we expect is to have, if we slide this stripe pattern, it does not cost energy. Also, because we have a finite size system, if you slide this crystal pattern, there should be particle flow that puts atoms in the end of the crystal and puts them back to the other position. So we quantify this by what we call the imbalance. So it's the difference in population between this peak and this one. And then the position of the pattern, you see this D, central of the pattern. And we see that there is a very clear linear correlation between the two. And what was shown said in the dipolar supersolid experiment is that this linear relation between imbalance and displacement could be interpreted as evidence of the Goldstone mode. That's how the dipolar supersolids say there is a Goldstone mode, just really by doing this type of measurement. So seems our striped supersolids do the same. So now, I mean, we have seen that there is this crystal emerging, that it can appear in any location. There is particle flow when this crystal is moving. But of course, this is only one set of characteristics of the supersolids. It's just like the crystalline part, let's say. But we also want to see whether this system is still superfluid. I mean, we hope it is because we started from BECs, but it would be good to cross-check. So for checking that, what we did is to take our system and look at its response to compression. So you take the system, you compress it, and you see its width that we can also extract very well from these images, oscillating in time. And we know in BECs that a proof of superfluidity is actually the frequency of the breathing mode in the system. So what you expect is that this breathing mode frequency is square root of 5/2 times the trapping frequency. Then you have a superfluid. If it differs from that, you would have a thermal gas, and or a non-superfluid, yeah. And here what we find, the value that we measure in this experiment, is really in rough agreement with that. So, I mean, the excitations seem to really show that the system is superfluid. Not just we expected, but it's really what we see. And also there is something funny that happens. If we compress our system, then you may wonder what happens with the number of stripes. And what we see, if you focus here, this small bit, is that the number of stripes is changing over time. So we can go between like something like 8 stripes to 10 stripes in these conditions where we did the experiment. It's the number of these blobs that fit in the size of the cloud. So this is, again, an evidence of flow of particles when the crystal changes. So this is all nice, but then we wondered, okay, how is really our stripe pattern, this crystal? So in the cavities, it's rigid and it's incompressible. And there were many people in the community thinking that this would be the same in the spin orbit coupled BECs. And it's probably just an analogy thing, because the cavity, this supersolid, is induced by light and it was rigid. Well, the spin orbit coupled BECs, they're also light induced, so it should also be rigid. So this is written in many, many papers that, okay, the crystalline structure externally imposed, it's rigid lattice, no excitation, and all these things. Atoms are always localized at the same distance from one another. This is what you often get from experimentalists. It's the naive expectation. But if you ask a theorist, well, they tell you different. It's more complicated. Actually, you need to be more careful about that. So they were expecting some excitations. So we thought, well, this is something that we should cross-check in the lab. And for that, we just made our system, and we wanted to know whether it's possible that you have your crystal and it has a spacing that changes over time. And just for checking that, the only thing that we had to do is to prepare the system, instead of getting adiabatically in the phase, a bit too quick, such that we don't prepare it in the ground state. There are some excitations in there. And then we immediately saw this in the experiment. So we enter into the phase, and then as you wait, you see oscillations of this crystal period. So why is this happening? Actually, you can understand it very well with the dispersion relation. So the crystal just comes from this difference in momentum of the two minima, and now with the atoms, because you are a bit out of equilibrium, they are sloshing in this minima, then this momentum difference changes, and then the inverse of that, that's the crystal spacing, it really changes. That's what we see. So in other terms, you can say that this stripe compression pattern, it's actually, this mode is actually nothing else than the spin dipole mode of these dry states, this left well and this right well, so they can oscillate out of phase, and that will make this compression and expansion of the crystal. So you can also go beyond and then also check what are the theory expectations. And what they really expect is that this stripe compression mode has a frequency that vanishes when you exit this supersolid phase. And then when you're out of this phase, of course, there is no crystal, so it cannot have a period that is changing. And there are also another mode that occurs here, which corresponds to the two minima, like oscillating in phase. This softens much less because this is nothing else that it comes from the curvature of these wells. So it will only vanish when actually the two wells disappear and you have a single well. So actually by checking these modes, it's nice because you can see the different phases. So you can see whether you are in this stripe phase or in this plane wave phase, so supersolid, no supersolid, and also whether you have two minima or one minima in this first relation. And this red softening here was already measured quite some years ago in the PAN group. But what we want to do now that we can see the stripes is to look at this other mode, this spin dipole mode. And for doing that, we actually move from real space measurements that we were doing until now to momentum space measurements, because with that we can get more accuracy to really look what's happening close to the phase transition. So how this measurement works is that we have our system, and then we prepare it in the supersolid phase, and then at t = 0, we just switch off the Raman coupling and project the dry states back into the bare states. So you see, I mean, the left well will project into up and a bit of a mixture of down, and it's the opposite for the right well. and then this down is really having a lot of momentum, so it will fly far away, while the up here has a little momentum kick just from the difference of the dress state minimum position to the one of the burst state. Yeah, and the same for the other well. So if you then just do time of flight expansion with a magnetic field gradient, you really see these 4 momentum components, and now you can check how they are moving together or how they are moving out of phase. Very simple measurement, and that's what we find. So we really find the frequency of these modes. The dipole mode is softening little, effective mass effect. It will soften only, go to 0 only when we go out of the double well dispersion relation. On the contrary, the interesting one, which is this one, the blue one, this is the compression and expansion of the stripe pattern. This is really having a frequency that decreases, and goes the lowest when we are essentially at the phase transition. In practice, I mean, it's very hard to measure exactly here, because you see the type of data that we get is like this. So we see oscillations in momentum that have a frequency that clearly slow down as we are increasing the Raman coupling. But at some point when we get very close to the transition, I mean, the oscillations are so long that they start to come close to the system lifetime, and then we cannot measure anymore. And then maybe the last thing I want to tell you on that is that, of course, this we do for one particular combination of scattering lengths, but we have all this tunability with the Feshbach resonances, so we can also change the magnetic field such that we change the values of these scattering lengths, and then we expect the stripe to plane wave transition point to move. Yeah? We can compute that theoretically, and really the points that you are seeing here are measurements for these 3 different lines, and we can really see, I mean, normally we do measurements in a regime where the stripe phase is quite stable, but we can go to a less stable configuration or even more, yeah? And you see actually what we find. And one thing that I should emphasize, actually these points are the measurements, but the solid lines is really the theory that we can make analytically, assuming this mixture picture, let's say, for the excitations with no fitting parameters. So this is really working pretty well. Okay? So with this, I really come to the conclusion of this main part of my talk. So I hope I have convinced you that we can now make robust supersolid stripe phases in spin orbit coupled BECs, and the trick that we have is to use potassium 41 atoms. And then we have looked at different aspects of this supersolid-like phase. So the first thing is that using matter wave lensing, now we are able to look in situ at the density modulation and see directly this stripe pattern. We can measure its period versus the system parameters. We can also check whether the system is superfluid or not from the compression mode of the gas. We can go more in depth into this stripe pattern and look at its compression mode. So see that the spacing, it's actually compressing and expanding over time when the system is excited. And then we can also use that to see the frequency of this mode, how it decreases when we get close to the phase transition, really to pinpoint where we go out of this supersolid phase. And now what comes up? So there are many things that we can play around with this system. Of course, we can investigate better the collective crystal modes. I think what would be very nice is to have a more direct measurement of this Goldstone mode. So we do the same measurements that they do in dipolar gases, this imbalance versus displacement, but we would like to really start with the stripes always in one location by artificially pinning them there and then letting them move and really see this lysing that I think would be some much more convincing proof. Another thing, we have seen that the system is superfluid, but it would be very nice to measure its superfluid fraction. So there are some ideas around on how we could do that by checking the amplitude of this density modulation, checking the collective modes also of the system. And there have been experiments in this direction done in lattices that could be now generalized to our supersolids. Then, to me, one very important thing is to go beyond the mean field approximation. So really try to see beyond mean field effects in this system. And this is something that in dipolar supersolids cannot be switched on and off. I mean, in their systems, for the system to be stable, they need the first beyond mean field correction, the so-called T1-Yang correction, to be there. In our system, we can have it there or not. So we can go in a regime similar to experiments that we did many years ago, where we can almost cancel out completely the mean field terms, such that the beyond mean field terms are important. And in this regime, that's where we were able to see these ultra dilute liquid droplets. And now we can put spin orbit coupling on top and see how they interplay the spin orbit coupling and the quantum fluctuations. And this is something that should be really realistically within reach in our experiment by changing again to the other isotope, the potassium 39. And then the last thing, and that we are already working on that, is to try to look at the interplay between this self-established density modulation and some external optical potential, really to look at what happens if these potentials are commensurate or not, really this interplay between the two orders. And with this, I want to give credit, of course, to the people that did this work. So this is the potassium team in my group. And these experiments were initiated by Craig and Ramon. They saw the first signals, but really all the data that I have been showing today was acquired by Sarah, Vasily, and Remy that really pushed even forward these experiments. And we had a nice theory discussion and collaboration with our theory colleagues at the Autonomous University of Barcelona, Josep Cabedo and Alessio Celli. And this type of problems were part of the PhD thesis of Josep. And now we have new team members that are really pushing for better imaging, for the lattice, for the beyond main field effects. Andreas and Ignacio, that maybe quite some of you know because they come from here. And with this, I want to just take a few minutes to advertise a bit what we do in a second lab in my group. This is our Strontium quantum gas microscope lab. So this is a lab that just came online. It's 2023 were really our first results and so on. We have a very compact strontium quantum gas apparatus. If you are interested in the details, you can just read this technical paper that we wrote. And what it has is this tiny glass cell with strontium glowing in there. And we have a commercial 0.5 NA microscope just very close to the atoms. So it's very simple system also to build. But we have a lattice around. Our lattice is made at the clock magic wavelength, so 813 nanometers with a fourfold configuration such that we have 575 nanometer spacing. And this, with the NA of this commercial objective, is already enough to, in principle, see the different lattice sites. So how we do things for the imaging is just really like in the tweezers. So we just we just shine light on the 461 nanometer transition, the broad transition. This is for the fluorescence imaging, and these are the photons that we capture with the objective. But at the same time, we cool on the narrow transition, the 3p1 transition, using attractive Sisyphus cooling. So the main difference, I think, what is done, for example, on the lattice tweezer hybrid experiment here is that we use attractive Sisyphus cooling instead of repulsive. But it works well also for our small lattice spacing. So you see here some of our first images. These are images that are taken with a thermal gas and where you can see the single strontium atoms. And for these experiments, we are using strontium-84, and we use strontium-84 because it has a scattering length that is similar to rubidium. So we can also make Bose-Einstein condensate. And when we make BECs, then we tried our matter wave lensing tricks that now we like also from the other experiment. And we can see the momentum distribution of the system and really see interference peaks, superfluid emerging. So if you're interested in the details, because I skipped almost everything, you can also check our paper that is online. In principle, it looks all numbers are good enough, like we have fidelities of 95% for the reconstruction between like two successive images and so on, so we can start doing physics. But actually, we decided to start 2024 by moving our experiment from the bosonic to the fermionic isotope, and we are doing good progress because we really start to see our first images of single atom result detection of fermions, and that's an excited system because we have 10 internal states, all with the same scattering length. So it's a nice platform to investigate SUN Fermi-Hubbard models. And I should also give credit to the people that did this work. They are all very smiley here because we hope we will do nice physics on all these things in 2024. So 2 PhD students, Jonathan and Sandra, that built the machine. So Jonathan really is the hero that started with the lab completely empty and built all this, and he's defending his thesis in 2 weeks. and two postdocs, Vasily and Tony. Tony, maybe quite some of you also know. And now we have a new PhD student, Carlos, that is pushing like crazy the fermions. So I hope it works also very, very soon. And with this, I want to just show you the complete group. I was telling things mostly about the Potassium lab, which is a collaboration between my group and the group for the theory of Alessio Celli at the Autonomous University in Barcelona. And I was also showing a glimpse what's going on in the Strontium lab, and the Rydberg lab will be for another time. So I would like to really thank you for your attention, and I will be very happy to discuss.
Thank you, Leticia, for this beautiful presentation and also very clear presentation. So now the floor is open for questions. We will be using the microphone, so Emmanuel.
Yeah, thanks for the great talk, Leticia. I was wondering, so what's the lifetime of this stripe phase actually that you observe?
It depends on the Raman coupling that we put. It can be like 40, 50 milliseconds. This is kind of a typical thing. If we go to smaller coupling, it can live much longer. So we can have hundreds of milliseconds, but with smaller contrast.
And this is determined by the scattering rate?
So this is really now intrinsic, because it's really because we need to go at this tune out in between D1 and D2 lines, and the splitting in potassium is 3 nanometers. So we did efforts of filtering resonant photons and so on. So we are really at this limit. And another improvement that we are doing on the experiment is to move from the red to the blue transition, because then we should again win on lifetime. But we have not yet tried on the others.
One other question I had on the modes, on the collective modes, you mentioned a lot of them. What about an amplitude mode? Is there something like an amplitude mode here?
Yes, but it's not... there is much less clear theory on that. So we are discussing with the group of Sandro Stringari that did a lot of the theory on these modes. We can compute some of that, and the data is very noisy, but maybe we see a bit of these peaks. The point is that this amplitude mode, it's a Higgs mode, it gets damped by mixing with other modes. So I think we don't have yet a clear picture whether we can have a good parameter regime where this mode will not be overdamped. And I think what we are seeing in the experiment is the regime where it damps very much with other modes, so it just has this decay and so on. They have also calculations in Trento, and we are discussing and seeing whether we can push for that. This would have a fast frequency, so that's also good, because we would be able to see it really within the time.
Oh, more questions. Rudolf.
Yeah, thanks for the beautiful data. You were talking about plane wave phase and the stripe phase. Of course, in between there is a phase transition. Is it really a phase transition, or is it a crossover? And also in a thermodynamic point of view, are these thermodynamic phases really, or what kind of phases are you talking about?
These are all very good questions. So these are really thermodynamic phases. You can really look at the thermodynamic limit, and they stay there. The transition between plane wave and stripe phase, except in some small parameter regime, is first order. So these are first order transitions. And this is actually something that is a bit tricky for detecting these things, because it's very easy to get trapped in metastable states. So for example, when I was showing these frequency measurements with the mode softening, there we really do experiments where we actually change also the polarization of the gas, so the spin composition of the system before we load into this phase, to be sure that we reach the ground state. We are close to the ground state, and we follow the ground state, because it's very easy to get trapped in metastable states that really live very long, comparable to the lifetime of the experiment. So this is extra tricks that you need to pay attention to. But it would be nice, but I think we need to extend the lifetimes to try to see hysteresis at the phase transition or things like that.
Okay, great. And what you have a finite size system. What what role is played by the finite size of the system regarding phase transition and thermodynamic phases?
Well, that's a good question. Of course, we should be careful with talking of the phases, because the system is small. I would still make the disclaimer that it's much bigger than in the dipolar gases, because it's like we have at least 10 stripes. They have like 3, so we have a bit less of finite size effect. But of course, it would be nice to scale up larger. I think for the moment, it's not so easy. I don't see super immediate. I mean, there is no fundamental problem for us to scale larger, except that we will need to optimize more the experiment, have larger atom numbers, and so on. We also chose this relatively large spacing of the stripes just to see them more easily.
I just was wondering, I'm quite sure that theoreticians could calculate the finite size effect.
They could definitely, yeah.
They definitely do, okay.
Thank you, Leticia. I was wondering that the ground state properties seem to be kind of pretty independent of the trapping potential that you have, apart from the overall density distribution. But the excitations seem to actually depend a lot on the trap. Would there be a difference when you go to, let's say, a box potential where you don't have any characteristic trapping frequency?
So if we go to a box potential, the good way of understanding the system, and we did numerical simulations, but we did not do anything, would be to really look at sound propagation. So we could put a defect that couples either to the spin degrees of freedom, basically, or density degrees of freedom of these stress states. And what you see are really like the two Goldstone modes. So you have excitations of the crystal and excitations of the overall density. And that would be the good type of probes, I would say, in a box potential. So we really run simulations. Also, you can do rings because then it's nice. You can have basically no boundaries. But these are, for the moment, I would say, things that we do on the side. We are also writing a theory paper on that, but it would be pretty hard to do in the experiment. On the other hand, I have to say these harmonic traps, this is something that Sandra Stringari always advocates for. These finite side systems have also the advantage that the collective modes in these traps can be used as proxies of superfluidity and so on. So a lot of the conclusions that we can extract and say, for example, that the system is superfluid right now, come from the fact that it's harmonically trapped. So I think it's like for the next round of experiments, we should look at better trapping configurations.
More questions? So maybe a question from my side. So I'm curious to know how you implemented displacement to then measure the imbalance. Is just displacing the...
So it's very easy because we don't do anything. So each time we repeat the experiment. I think this is also different from dipolar systems because the dipolar systems, because they are smaller, actually the stripes, they're most of the time in the same location. They have much less occurrences away from that. In our case, when we repeat, it's always in a different place, the stripe. So we don't do anything. We just take tons of data and we just then analyze it afterwards. So it's the easiest possible experiment, let's say.
Understand. Oh, question.
So in the phase diagram you showed for potassium, which is nicely accessible, it also looked at high strength, coupling strength, almost like there's some depolarization happening. Is that like where it's not a pure plane wave phase? Maybe I
don't know how it shows here, but there are actually quite interesting things that you can do if you go to the very large limit. So we put ourselves on purpose in this regime.
Yeah, this one, like on the right side, it seems to start mixing. Is that another stripe phase that appears, or?
This is the stripe. There's the plane wave here. So the perfect set 2 symmetry breaking, of course, only occurs on this line. That's if you're exactly on this line, you can choose equally likely one minimum or the other. Otherwise, you always fall in the one with the lowest energy. And here, what you are seeing is the single minimum transition. So it's really this thing that you have 2 minima, and at some point, they go to a single minimum. Yeah. And what is very interesting in this system, if we get lifetimes a bit longer, we should really look at that, is that you can tweak parameters such that you can have the stripe phase touching this single minimum phase. So you can find a 3 critical point where the 3 phases are mixing together, and then you can go to a regime where you transition directly from stripe to single minimum, which would be you have these stripes that are always stable, and then at some point they space so much that the spacing is bigger than the size of the system, and you fall into the single minimum. And there are some nice predictions on these things, also from Sandra. I think that's the very first paper that they wrote on this stripe phase and this spin orbit couple phase diagram. But if you look in rubidium, you would need densities that are completely out of reach. While here in potassium, it's just we could tweak a little bit more the parameters. We actually did on purpose that we have this plane wave because we wanted to see the softening and so on.
Okay, so if there is one more question, perhaps the last question. I know.
Yeah, like, is there like a plan to extend this into 2D where you can have all sorts of fancy like spatial, like pattern you can like, exhibit rather than just like simple 1D like stripe base?
This is also a very good question. So we are looking into that. We actually have together with Alessio a master student that is working on these things. So in principle, if you want to go from 1D to 2D, you need to add states because you need to have, you have these two states and you break the symmetry in one direction. If you add an extra state that you also couple, you can also break the symmetry in the other direction. And then, this is just to make a more complicated dispersion relation. The limiting factor right now, in theory, everything works very nicely. You can write down things, it works. But the limiting factor is if we add more Raman lasers and more states, of course, we also add more photon scattering and more heating. So we are also looking at a scheme for reducing this, like being able to have a reasonably large contrast of the phase with less intensity on these lasers, and it's work in progress. So we think it should be possible. I'm not sure if we will do the experiment, but we will put some theory out for sure.
Very good. So before then thanking the speakers, just an announcement. So if you, one thing first. So if you didn't put a signature, then please put a signature on the form. And the other one is that the next MCQST Colloquium will be given by Professor Mark Saffman from the University of Wisconsin. And this will be the Tuesday on the 28th of May. So save the date. And at this point, I would really like to thank Leticia for coming here and for the great presentation. And also Ronan, thank you very much again.